How are you? Adi, check your line. I sent you a link to join the Senior Project 2 line group.
Yes,
You saw already?
yes.
Yes, join that group. There are other students too, so we can, talk together and take benefit from our discussions more. So connect this. Wait for your friends to come. I'm gonna make a cup of coffee while your friends join me. Very nice weather today, right? Coffee. Wait 2 seconds. Oh, I thought I had the mic on. I was talking. Where is my camera? Okay. Good afternoon to you all. Am I recording or not? Yeah, this is being recorded. So let's start. So Adi, did you hear what I said, or my mic was off? I said join the line group. You heard, right? Okay. All right. So let's check the attendance first. Okay, we have Audit is here. Nata Chanon.
Yes.
Yeah. Yeah. Shashank. No. Eldad. Eldad is here. Okay, Eldad is here. Eldad is here. Konsu is here.
Yes.
Korabi K.O. Korabi is here. Yapping is here. City. Oh, okay. All right. So I graded your last week's reports. You can go on LMS and check. Those who did not submit in PDF, I cut 1 more. Okay. Submit in PDF format, because if you do, then I can easily, when I open the website, I can see it and I can just comment on it right on the spot. But if you give me other formats, I have to download it and open it, and then I cannot give you feedback right on your report. Okay. So PDF is the preferred format for your report submissions. Is there any question that you have? No questions?
Sir, I want to ask about the line group. What do you mean by line group? Because I couldn't hear.
Oh, no, not you, not you. Only the audit, because he is my senior project advisor. So.
All right, sir.
Yeah, I sent him a message, but he didn't join. I asked him to join. So, yeah, not about you. So let's see where to start. So let's save this one. Let me get my coffee. Hold on. So where is this? This is here. Okay. So in morning session, one student dropped, and because of that, I talk about. It was a series of thoughts actually came to my mind, and I spent like 20 minutes talking about them. It was about, but I think it's good if I share it with you guys too in afternoon session, so it will be fair. So one student dropped, and then I remember myself, because when I was in my undergrad courses, yeah, what happened was that if my father wanted to send me money, if he sends me $1,000, I could get 30,000, something like around 30,000 baht, okay. But I'm from Iran, so we have to fight with America, and then they put sanctions on the country. Sanctions. Oh, it's raining. Hold on, my dog is outside and it started raining. Hold on a second. Oh. Come here, come. Come. Rain. Come. Okay, hold on a second. Hold on. Let me. Hold on a second. Yeah, do. Oh my God. Hold on. Again, one more time. Okay. All right. Go. Disaster. Oh. Okay, I'm sorry. I'm back. Oh, I was not expecting this. The weather is very beautiful today. So the first time I came to Thailand, the weather was like this, and that made me fall in love with Thailand. Very nice weather. It's like rainy season, not very hot. Anyway, so let's talk about this. Yeah. So I was in my first year of studies in 2011, and they put sanctions, and all of a sudden, two third of the country's currency value went down. It means now the local currency that my father could translate, convert to 1,000, now 2/3 lost. So it became this much. So instead of 30,000, I could get 10,000, right? So what is this? This is actually called hardship, right? So the hardship really drive me. That was the driving force, okay? To study so hard because I knew that if I get a GPA of 3.85, I can get a scholarship. So the hardship actually drive me to go for this. Otherwise, I was like a lazy student. I would be happy with a GPA of 3. But I knew if I go through that path, then I cannot actually get the money from my home country, right? Because of the sanctions. So I actually pushed so hard that in third semester, I could get it. In third semester, I could get the scholarship. So if this is the lifespan of academic life, so 1, 2, 3, here I could get it. And all my bachelor life, and I got a scholarship in PhD too, and all the PhD until here. I study for free. And really, when I look back at this time, when I see people withdraw, the reason I'm talking about this because one student withdrew. Okay, it's like, oh, okay, maybe I cannot handle because I take a lot of courses or whatever. So I withdraw. But look what happened to me personally. When I was here, right, the withdrawal option was, don't even talk about it. It was not an option. I could not even think about withdrawing, let us start failing a course or no, not at all. I wanted to get a scholarship because I, couldn't pay. I couldn't pay. I had no money. Okay, and that drive me to show such a performance that I could actually get a scholarship all the way till now. Okay, now the question is this: is the hardship that I don't want to write this? Is the hardship the best driving force for humans or individuals in a society to work harder or more efficient way, or the prosperity and comfort? Prosperity. What do you think? Tell me in the chat room. What do you opinion? So you have a child, you have a kid. Will you, if you let's say you have money, enough money, will you give them car and buy them a house and put them pocket money in their pocket and buy the best watch and clothes and food? Or will you just tell them no, you have to buy your own car, go find a job, go study, and I'm not going to help you? What do you think? What's your opinion? Am I in line? Hello?
Yes.
Yes. Okay. So text me here. You can text here. So if hardship, you just say hardship or prosperity. What do you think? No, it's very easy to spoil a child. Yeah, audit is correct. Yeah, both is a good answer. Yes, actually that's the correct answer. Anybody else? For me, both too. Yeah, that's the correct answer. There, this is the engineering course, right? I hate kids, by the way. You were a kid yourself one day, right? So you have to actually, you went through that path one day, so you have to actually respect that lifespan because you were a kid yourself. Yeah, so this is actually the engineering conclusion. Hold on. So I'm gonna give extra points to audit 1, C report 1, and NATA channel 1. Okay. So the engineering point is this, that when you are faced in your life with 2 directions, either you want to go left, okay, or you want to go right, then remember what I tell you today, okay? The best way is to pick the middle one and go for the balanced position, right? You always have, even the nature does this. Let's say the population of rabbits increases. So this is unbalanced. And then all of a sudden, what happens is that they are actually food to the wolves, okay? And then the population of wolves increase in order to, because they have more food, right? And then they eat, when they have more food, they increase. And then when they increase, they eat the rabbit more. And then all of a sudden, the balance, actually the equilibrium will be achieved. And then the population of the rabbit will shrink. And again, the nature comes back here, balance. So, yeah, for your kid, if you have the money, the balance is like, okay, I buy you a car so you can actually go to university and come back. Why not? But not, to such an extent like I'm going to buy a car, maybe 2 cars, and then a house. And even, I will select your wife, no. So maybe just a car, but the house the kid himself must buy. Maybe after he gets his master's degree, you might say, I'm going to help you 20% of your housing cost, maybe, okay, something like that. Because if you provide everything to a person, then there will be no motivation. And that's actually what's happening right now in Europe for the last 4 decades, okay? You don't see any technology or innovation coming from Europe at all. There is nothing. The 5G comes from China. The AI comes from China. All the advanced stuffs that now the modern day is seeing comes from actually the countries that went through hardship. So after World War II, the EU, they set up some social security policies. So for example, individuals, right? If this is 0 income, this is maybe 10%, this is like 70%. Most of the people, if they like here, if something happens and they fall below 10%, then the government come and help. They help them. This is like the threshold. If you lose your job, you will get free money, monthly money, because it's like security for you. In the beginning, it looks very nice, right? Especially when you won the war and you just help all the population. But in long run, because people don't worry, there is no hardship anymore, so people don't worry about what's going to happen when I lose my job. When this go below, no, don't bite. When I lose my job or my revenue falls, not a big deal, the government helps. So why should I study so hard to get a scholarship? For example, in Germany, you can study, the one that you pay right now, right? If you were in Germany, the bachelor program was for free, the government supports. You can get your bachelor degree for free. So why really, study hard? You don't have that motivation. So the best answer is this. When I saw today this student withdrew, it really saddened me. What is the lesson 2? Balance, okay? Then the second right answer is actually hardship. I prefer hardship. Hardship, some people are not, on the same page with me on this, but this is my own personal life. I really experience it. Hardship is the one that drives people seriously, okay? But prosperity makes you lazy. When you are rich and you have everything, food, everything, that's why the kids, because they have food and accommodation, they play game. And the parents tell you, what you doing in your home, in your room alone? Come on, what you doing? They just don't care because they have everything, right? And then they keep playing. So, but there is an extreme here. So when you actually have nothing, total hardship, right? Then there will be severe damages, permanent damages, and then you actually cannot advance. Okay, so the hardship to some level is justifiable, but when you surpass that limit, then you destroy people. Now you look at the people in Afghanistan, it's a country here, Afghanistan, right? So here the people, the map, is here. Afghanistan, now the US just withdrew. They are in war. Either, the USSR attacking them or the Americans or civil war for 40 years, 4 decades. So now if my argument was right, then saying that hardship is actually good for people, right? Then here is ultimate hardship. Think about it. The Americans bombing you, the Islamists, radical Islamists bombing you. Everything is like total restriction. Girls cannot go to school. It's just, a lot of restrictions, and it actually will be translated to hardship, right? But if the hardship was good and the best driving force, then you would have a lot of doctors and PhDs coming from here, right? So you see, there is a limit into it. So those who said both, they are correct. This is actually a very interesting topic. So another analogy is about maybe asking this question, that which force do you think is more powerful, fear or love? Okay, it's actually not easy to answer. So will you, for example, move your ass and go outside to find some job if you have fear of, for example, not having food tomorrow? Or maybe you are in love and you want to get or catch your target girl? Which one is more potent? There are a lot of debates about it, but this is similar to hardship and prosperity, something like that. But the correct answer is both. But if you ask me, I think personally fear is more potent, really. Fear is more powerful. There is nothing more powerful than fear. Anyway, so back to this is actually, I talked to the morning session, then I thought I talk to you too. It's good for you. So you can actually get motivated when you feel down and you don't want to study. Then you think about a little bit of hardship that might happen to you if you don't get your degree. Then maybe that motivates you. Maybe. Okay, so do you have any questions?
No.
No, let's start. So far, we were dealing with a smaller scale integrated circuits, like 10, 15, 20. And the way that we deal with them was either, for example, use a pencil like this and piece of paper to draw a K-map, right? And optimize. Or maybe we did it in our head. Maybe we memorize some equations, Boolean algebra equation, things like that, right? And we could actually handle it because the number of the gates, pencil and pen, were less than 20. We could actually handle it. But later on, when the designers, here is around 1960s, okay? Then when the designers reached to 1980s, then they were facing circuits with about 100,000 logic gates. That's a lot. So here they had difficulty. How could they handle, debug, maintain, add the stuffs, and debug and deal with these huge circuits? There was a difficulty. So they had to solve this problem. So the solution to this sheer amount of logic gates was this thing that you see here, HDL. That's the solution. So basically what they did, they introduced CAD software. We call it CAD or EDA, computer aided design software, or electronic design automation, whatever you want to call it. Basically, they ask the computers that they build already by their hands to help them, okay? So they came up with a programming language and a software to help and assist the circuit designers, okay? So now look at this complex circuit. If I ask you this question, what does it do? Can you answer? No. What does it do? No. Because what you see here is a bunch of gates. And actually there is a term for this. We call it gate level. Okay? This is a gate level design. It's low level. So a low level design, when you look at it, you have no clue what the hell it does. You have no clue. Okay? That's the problem. The designs are getting bigger and bigger, and we want to make sense out of them by just looking at them for a few seconds. Later on, the circuit designers said to themselves, why we don't hide these logic gates, and instead of showing the gates to each other, we will just show a rectangle like this, a box, and then we put whatever it does, the function on it in English, you see? So in that way, we hide a lot of details, unnecessary details. And now if I ask you, look at this one and tell me what it does, then probably if you have a little bit of experience, you might be able to answer. What is this? Sorry, Ajahn, are you sharing the screen? Oh.
Oh, that's why.
So since the beginning, you didn't see my screen?
No.
Oh, no.
Are you joking? You are funny, man. So, you should tell me earlier. This is like 30 minutes. 30 minutes past, you just looking at my ugly face. How about now? This is so funny. And nobody tells me. So I was showing the Afghanistan map, you didn't see?
No.
Huh?
And all this stuff you didn't see? It's okay, so it's the beginning. So, oh my goodness, you have to tell me. So that's what I mean. Now you see my screen, right? If I show you this and I tell you what it does, you have no clue, right? Because this is gate level. But if I show you this, so the designers tell to themselves, we are going to hide the details, not showing the logic gate to each other, and instead we use, you see, a box, and we put the behavior of that circuit like this, okay? Now, Now you see my screen or not? Yes or no? So funny.
Yes, yes, now we see.
Okay, okay. So now, if I ask you, hey, tell me what this circuit does. You know, if you have a little bit of experience, you can see that this is arithmetic logic unit, ALU, and there are two operands coming from the registers, and then the answer can be saved in data memory or can be redirected back to registers, and then you have a bunch of logic gates. For example, the logic gates will produce the control logic, and ASEL will be used here and there and here. These are the logics three all coming from here. And this is actually the instruction memory that will be fetched. So instruction coming here will be executed. The result will be saved into memory or read back to register to be reused in next instruction. And all of a sudden you realize that, oh my goodness, this is a microprocessor. What I'm showing you right now is a microprocessor. And you can actually see it, and probably this one maybe is the equivalent circuit of this, but here if I show you this, you cannot tell me that this is a microprocessor, right? A portion of the microprocessor maybe, right? You cannot say. But here you can, okay? So basically what happened here? Here, by raising the level of abstraction, I try to hide the details and just show you the behavior, right? We call this behavioral modeling of a digital circuit, right? Now, this is what actually the HDL does, the HDL, okay? It tries to help the designers to express or describe the circuits without dealing with logic gates. They only can talk about a circuit or describe a circuit using some programming language to express the behavior of the circuit, not the logic gates. Now let's see what this H, D, and L stand for. H stands for hardware, D, description, L, language. So the designers actually had to come up with a new language. Now every language, you see the English language, we have to learn new vocabulary, right? So this is a new language and you have to learn. Over there, we don't call them vocabulary. We say, we call them keyword. So you have to learn the keywords of this new language, okay? Which is actually very lucky. For what? For describing the hardware, okay? Describing its behavior. You describe the behavior of the hardware. You don't use the logic gates anymore. Why? Because you want to tackle this sheer amount of logic gates here. I will show you later how beautiful it is, okay? Now, you already kind of use this technique, means hiding the details, okay? Or encapsulation. When you drew your first symbol of inverter, when you drew this one, the first time you drew something like this, you actually use this idea of showing the behavior and hiding the details, okay? So what's the behavior? The behavior, the only thing, when you draw this, you want to tell me, hey, you know, I want a device that behaves like an inverter. It means if I put here 1, I get 0. If I put here 0, I get 1. This is what I want. This triangle, right, and this bubble here does not exist in real life. There is no such a thing like this in real life. This is just a symbol. Okay, a symbol that represents the behavior of something else. What is that something else? That's the implementation of this inverter, which might be this. Okay, 2 transistors. So basically by drawing this, you just tell to another engineer, I just want an inverter. I don't give a damn about how you're gonna implement it. You wanna use a BJT transistor or a field effect transistor, or you wanna use a seesaw, whatever. I don't care. I just want this behavior. I don't care right now. But when it comes to implementation, I do care, okay? But it's like, let's not get into the details. Just give me this inverter and then I'm gonna make bigger things with it, okay? Now, even this thing is a symbol. There is no such a thing as this, right? This is the symbol of a PMOS transistor. Again, this is like a behavior of the PMOS, and this is a symbol. Okay, so what is a PMOS? You have to actually go deeper and deeper. You see? So this is the symbol, right? And what is it? Then you actually get to this point. It's actually this thing. There is a pink material, right? And the blue material connected like this is like a hole. And there is this pink material in between. And then there is this yellow material. And then another material. And 1, 2, 4, 4 different materials, like a sandwich. And then you get the pins. And this is actually the PMOS. Now, actually, there is no, can you see the N here? N pin color. There is no N pin color in real life. This is also a symbol. A symbol of what? A symbol of a semiconductor, doped semiconductor with extra holes. Or this one, again, another semiconductor with extra positive charges. Okay, so as you see, everything is like a symbol that represents something in real life. Okay, so how are you gonna make this? There are, again, implementation of this pink layer can be, you know, maybe 5 or 6 different ways to have this doped N and P type semiconductors. Many variations. But we, you know, somewhere we have to stop and say, okay, this is just too deep. I really don't want to get into that. Because if I want to go so much deep into that, then I cannot design big circuits, huge, complex systems. I cannot do that. So we have to actually stop somewhere. That happens everywhere. Even in hospital, you know, some people become nurse, some people become heart surgeon, some people become brain surgeon, different, you know, and then they have a barrier. They cannot serve, you know, they just cannot, their field has a border and they cannot cross it. If they cross it, they just got to conclude that they don't know anything. Yeah, so system designers, I mean, the digital circuit system designers, right? They really don't know the system. They know, you know, they know, but not the details, and they don't care. What they know is the system, okay? And the ones who design the transistors, they really don't know the system. They know, but they don't, you know, it's not their job to design the system, huge systems. Their job is to design this single transistor. Anyway, now, with this background, we are going to get our first introduction to HDL, okay? Now, if I go to Google, let's go to Google. And I type for HDL language list, here, this one. And look, how many languages do we have that falls in the category of HDL? Let's see. Look at that. Few here. Able, HDL, Chisel, Confluence, Ella, Handel C, Park, GHDL, and Lola, Lava, System C, System Verilog, and VHDL. And look at this. One of the most widely used and well documented HDLs. That's why we pick. This is the one we learned. But I just want to give you an overview. How many more there are? Can you see that? Okay. Okay, when you get into the industry, you will know more. Okay, now let's compare these two. This is actually the most widely used, right? So we're gonna compare these two. It's here, VHDL, very like. This one looks like the syntax looks like Ada. What is Ada? Ada is a programming language, supports parallel programming. Look, Ada, okay. Extended from Pascal. And it has this design by content. And it supports parallel program. Concurrency means parallel programming, okay? So this is very important because look at these two gates and tell me this. This NAND gate and this AND gate, are they being executed or run or behave or function in parallel or not? Are they in parallel? Yes. Elda? Natasha, no. This is the previous yes or no. Okay. Natasha, no. Yes. So that's actually the nature of hardware. Everything is in parallel. Can you see that? That's why they pick Ada, because the Ada supports it, supports this kind of behavior. Okay. But there is another one, the one that we actually use. The syntax look like C, but it has nothing to do with C language. Okay. Anyway, but both of them support gate level data flow behavioral modeling. Okay. And this one is harder to use. This one is easier to learn. So that's why we picked this one. Okay. But really, if you ask me personally, I prefer VHDL. I think VHDL is better. Anyway, your DLD instructor, before it was Dr. Kong, he actually uses Verilog, right? Now it's changed. There is another instructor, new instructor teaches this one. Before I used to teach this one, but this semester they hired a new one. And I think I saw the textbook. He also uses Verilog, so that's why we pick Verilog. Okay. Now a big warning here. Take this seriously. Okay, warning. You know the C programming language, right? When you come to this course, you have to code in Verilog. And Verilog, as you see, is look, the syntax look like C, right? Look, same. But it has nothing to do with C. And when you want to program in Verilog, you have to erase everything that you learn. Erase not permanently, but put aside. Okay, don't take any assumption from C programming language to here, to this class. So there is nothing about C programming language. Why is that? Why? Look at this. We have two kinds of computer languages. Both of them are language, right? Language. One is called software programming. Another is HDL, is hardware description. The one that I just told you on title, right? Here, HDL, okay? Now let's see what's the difference. Now I'm going to show you a few lines of C code, which is software programming language. So if I want to write C code, I write something like this: int A is 0, int B is 12, int C A plus B, right? Right? So what happens here? Here you have a compiler. The compiler gets this code, converts it to machine language, and then it executes the code line by line. First this one, second this one, and then this one. Now, if I change the sequence, okay, then everything will change. Can I change the order of these lines? No. So this is sequential. The sequence does matter. You cannot change this. What is this? This is programming language. It's sequential. Okay. Now, let's talk about HDL. I'm going to give you one example of what HDL is. Okay. Now, think about this pen. This is the pen. Okay. It has a rubber here. And this is the carbon, the tip of the pen. Okay. So now I want to describe this. So I say pen is blue. The height is 20 centimeter. The diameter is 0.002 meter. Whatever. The height, diameter, and then maybe the coating material is wood, whatever. So I start to describe this thing. So what else can we talk about the pen? Yeah, that's enough. Okay. So what am I doing here? Here I use a language to you see the D here? Now I'm describing. What? A pen. I describe a pen. That pen is actually hardware, okay? Now, will it make a difference? Instead of this order, 1, 2, 3, 4, okay? Instead of this, I write this. I say diameter is 0.002, coating material is wood, pen is blue, and the height is the height, I think is wrong, should be like this. 20 centimeters. Okay. Tell me, will it make a difference or not? Tell me in the chat room. What's the answer? Hello? No. Yes, not the channel again. No. It makes no difference. So simple, right? If I first say state the color, or I tell the color on the third line, makes no difference. It's very important to understand this, right? This is the difference between HDL and normal programming language. Here, there is no order. Everything is executed in parallel. So if I say put an OR gate with input A and B and the output C, and then connect the C to an inverter. If I talk, now you still don't know how to write this in HDL, so I just write the symbol. If I put this first and then put this second, versus I put this first and put this second, it makes no difference. You put this on top of this or put it on the left, on the right, makes no difference. Does it make sense? This is actually so simple, but the students who do not pay attention right now to this, right, they will have enormous difficulty in this course because they keep seeing this C-like syntax and they think it's sequential and then they get confused. In HDL, we don't have sequence, no sequence. Everything is in parallel. Put this in your head, okay? Now, with that established, the head thing, now let's see what is Verilog. Let's learn Verilog. And there is nothing better than doing if you want to learn something, right? So let's do it. What do you want to do? We want to design a fairly, actually it's not complex, but for us, we are beginner, right? It's complex. We want to design a 4-bit adder, okay? So I wanna do this because I wanna teach you hierarchical modeling in Verilog. The hierarchy. What is hierarchy? Hierarchy is like you have something and then you divide it. Let's say this thing, okay, and then you call it a child, and these children are, you know, if you want to pay attention to the hierarchy, they have parents, right? 6 children. Now, this thing becomes the father that, for example, is responsible or holds or brings salary to these children and feed them. So there is a hierarchy here. There is the father and then the children, right? And maybe this child has also, you know, some other things under him or her. So that's the meaning of hierarchy. Now we are going to use this model, right, in Verilog to design this 4-bit adder. How? Design this 4-bit adder. How? Very simple. We need a 4-bit adder. So we are going to design a 1-bit adder and then multiply it by 4. Okay, so I'm going to show you how to do it. First, say hello to new keywords. When I introduce you to new keywords, I put them in pink color. Look at this. Module, input, these are like the new vocabulary of the new language. Module, input, output, and module, okay? So that's how I use it. You see in my code, they are a little bit bolder than others. So it means this is a special keyword for the language, Verilog language. Now, I say so basically what you do, you create a new file. So this is your file name with the extension .v, okay? So usually what the name of the module that you are going to define will be the like adder.v, okay? So you create a file, text file, adder.v, and then you put this thing inside this text file. And this is your Verilog code, Verilog code. Okay, this is the code. Now I'm going to explain to you the meaning of this code. First, you identify that this is actually a module declaration. Module declaration. Okay, so I define a module, and this is the end of the module. What's the name of the module? Adder. And this is called the interface to this module. So if you remember the combinational modules, they have this general format. Some bunch of signals go inside, so this is in, and some bunch of signals come out, right? So this one actually defines the name of all signals, the interface, and then here, this next line, it defines which one is input, which one is output. So if I write something like this, it means now my module, the name is adder. Then it has A and B input. So usually people don't put these arrows here, arrows head. The input is usually on the left. The output is on the right, okay? So the output is Cout and sum. So if I write something like this, it actually will be translated to a module like this. Now, if you pay attention, we have actually 2 kinds of signal. One is just a single bit, which is, we call it a wire, single wire. Okay. Another is a bunch of wires that are related logically together. They are also wires, but they are related. Maybe all of them carrying the bits of one signal, 8-bit signal, for example. Okay. We call this a bus. This is a bus. Okay. Not bus, bus. So now if you want to define a bus, here, for example, A is a 4-bit bus. So here you show it like this, 4-bit, 4-bit, sum is 4-bit. Why is 4-bit? This is actually the way that you show it. You open a bracket and this is the MSP dot column, okay, and LSB. So I give you one example. For example, if you have 3.0, this is 4-bit because actually it has 3 to 1 0 bits, okay. If you have 31.0, this is actually 32-bit. So 31, 32, all the way to 0. Okay, so you, by putting this column here, right, you just try to hide all these numbers in between. It will be translated to column. Okay, now we define this. This is our module, right? Now, after that, we have to define the behavior of the module inside this. HDL modeling will go here. Okay, so this is a standard. Now let's talk about what goes here. Now this is a 4-bit adder. I told you I'm gonna design a 1-bit adder. So this is a 1-bit adder. A, B, each one is 1-bit and C in. Now I show you the truth table, A, B, C in, right? And the output, this is actually sum. The output sum, and this is the C out. Okay, so it's very simple. A, B, 0, 0, 0, 1, 0, 1, 0, 1, 1. Okay, let's say if there is no carry, so everything is 0. What's the sum of 0 and 0 is 0. What's the sum of 0 and 1 is 1. Sum of 1 and 0 is 1. Sum of 1 and 1 is 2. 1 and 1 is 2. But I cannot show it, so I put here 0 and I set the carry to 1. Otherwise, the carry is 0. This table is called full adder. Can you design a circuit? The answer is yes. You use a K-map for sum. I'm not going to do it. For C out. 2 K-maps, right? And then you get the equation and you establish the circuit, right? The circuit will look like this. Full adder circuit. That's it, okay? That's it, okay? This is it. It's just a bunch of gates, right? But the thing is that we can actually design it. We have the ability to design it, okay? So now we design with paper and, oh, what happened? So with paper and pencil, we can design it, okay? I just show you, it's so simple, right? But can we design a 4-bit adder? The answer is no. Because now this thing, how many input do I have for a 4-bit adder? How many input? Come on, it's 4 bits. 4 bits. Each operand is 4 bits. 3? No. 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 Are you serious? This is a 4-bit adder. This thing is 4-bit. This thing is 4 bits. So you have 8 input. 8. Yes, finally he said 8. Natachano. 8. 8 input. So now if I use this simple thing, right? Very simple, right? Just 4-bit adder. Now if I want to optimize what goes here, right? I have to say A0, A1, A2, A3, all the way B0, B, oh, 8. And do you know how to optimize an 8-input kernel map? It's just so difficult. So difficult. You're gonna go crazy if you want to do it. Okay. So now you see, that's why I told you in 1960s, when they reached to gate levels like this, like 8 input, 10 input, they couldn't do it. Even right now, nobody can do it. Okay. So what's the solution? I'm going to show you the solution now. Okay. So they said, okay, I'm going to design a 1-bit adder. This is 1 bit. So this is again module and module. This is full adder. We call it full adder. Okay. We have half adder to go and find out yourself the difference. So you see A, B, C is the input and output is C in and C out. Okay. Now something must go here. Okay. This is actually simple. I just show you. What should go here is this. This should go there. But because now we don't know this Verilog syntax, let's just trust me. It's just so simple, right? It's just one line of code. But I'm not going to show you now. Let's assume that we put it there. So the implementation is actually here. So it means now we have a full adder, working full adder. Okay. Now look how easy it is. Now for the 4-bit adder, the only thing I have to do is we call this module instantiation. You see, the only thing I have to do is to declare 4 instances, 1, 2, 3, 4 of a full adder, and this is the instance name. So this is F0, FA0, FA1, FA2, FA3. Okay. When I write 4 lines like this, I will get something like this. Okay. Now, the next step, each one of them is a single adder. The next step is that this is the carry out of this, and I want to connect it to carry in of the next stage like this. Okay. What do you do in real life if you want to connect the modules? Can you tell me? What do you do in real life when you want to connect 2 things? I'm a puppy girl in a puppy world. I want to connect 2 modules. La 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 la. No, 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 no. Series? No. What do you use? How do you connect 2 things together? Come on. Wires. I'm a body girl in a wire world. It's not a channel. Gives good answers. You can beat my heart. Oh, Nata Channel is right. Nata Channel is right. Wire. In real life, you use wire, right? Say hello to wire. This is a real keyword. In Verilog is wire. You see, it's in pink color, means when you program, you can actually type wire, and then the software or the CAD software or the system will give you a wire. Okay. How many wires I need? 1, 2, 3, right? Look at this. This is the complete code. Wire. Can you see I use a wire and I have 3 wires. This can be anything. You can call Apple TV, whatever. But basically, the output here, right? The output here is carry. So I just say carry 0, carry 1, carry 2, the wire that I use, okay? So that's why carry 0, carry 1, carry 2. Now, you see here inside, I have to connect, this is the instance name, and the instance, I have to connect the pins. You see these pins, right? To other pins. That's how I do it. So what's the first argument? Look at the definition. The first argument of a full adder. This is it. What? No. What is it? Input A, right? Remember, second one, B. Third one, carry in. Fourth one, C out. Fifth one, sum. You remember this sequence, right? Now, the first one is A. Second one, B. This one is 0. 0 means ground. Okay, so basically carry in of the first one is connected to ground. This is ground. Okay, now carry out is connected to a wire. You see the wire? Now the next stage or the next line, I connect this to the carry out of the previous one to carry in of the next one. When I use the C0 here, and I use the C0 here, it means both these are connected, right? And this is a wire, right? So look at this, C0, C1, C2. This is ground and this is the output. Can you see that? Can you see the pattern? This is A0, 1, 2, 3. This is operand A. This is operand B. And this is the output sum. Okay? If you write this code, you get this. And this looks like a chip or IC, TTL IC. It's same thing. So basically, this is ground. This is my C0, C1, C2. This is, for example, A0. This is B0, A1, B1, and so on. And this is S0, S1, S2, S3, and this is the C out, carry out. Wow. This is called Verilog hierarchical modeling. So I use the smaller modules and I connect them together with wires and I built a larger module. Does it make sense? Questions? Somebody message me, let me see. Hold on. Okay. Right now. Right now, what time is it? 2:30. Okay, no time. Right now, you really don't fully understand why we need these numeric literals and why we need to use them, but later on you will see actually they are necessary. Okay, so if I have a wire in Verilog, I want to put 1 or 0 on it. Okay, in order to actually I want to, for example, put 5 volt or ground to represent high voltage or low, high logic or low logic, right? What do I do? If the wire name is Apple, okay, I can just say Apple equals to 1. Exactly like this. Semicolon is like C code. When I do that, this wire actually will hold the voltage 5. Okay. Now this is only one wire. What happens if it's 2? Okay. So here it becomes Apple 0. So I will introduce an index and Apple 1. Okay. Then here, when I want to say, for example, I want to put the value 0, 1. Okay. Then I say signal Apple equals to, now this is 2-bit single code. What is this called? Public, yeah, single code. System is binary, and this is actually 1, 0. So 0 goes here, 1 goes here. This is actually the value 2. Okay, but the way that I have to represent it in Verilog, this is the complete way, is first. So let's zoom in. So this is how we do it. First, you tell the system how many bits your literal is, then the system binary, and then the value. Now, if you pay attention, there is this underscore. Underscore is nothing, will be ignored by the system. It is just for us humans to distinguish. So if I have a lot of 1 and 0s like this, okay, then I can simply put underscore every 4 bit to help me see. You see, I can actually read this easier, right? So what systems can I put? I can put decimal, binary. This is base 8, octal, and hex is base 16. Binary base 2, decimal base 10. Okay. So another example, for example, 32-bit system is hexadecimal. Now means I can, every digit is 4-bit. 4-bit. I can put from 0 all the way to F, right? Because it's hex, H is hex. Now, to your surprise, there is this X. What the X means? Means the value is unknown at that location. Means I really don't care about what is it, it's unknown. What I care is that this should be 9 and this should be B5, okay? Now here you also can put Z. Z, what does Z mean? So if you have a DC voltage, then this is R and this is called resistance. But if you put, you talk about AC circuits, alternative current, go up and down, right? Then we don't say resistance, but the idea is the same, something that resists the current. We call it impedance, you see, impedance. So this one we call it with Z. Means what? Means it resists the current, it doesn't let the current go through, right? So in digital circuit, look at this. This is my wire, this is VCC, this is ground, right? Maybe ground, I use it, ground, okay? Now, if I connect this wire to here and I prop it, what do I get? Let's say 5 volt. If I connect it to here, what do I get? I get 0 volt, right? If I prop here on. Now, if I disconnect this, what do I get here when I prop? The answer is Z. I get Z, means high resistance to current, because this thing is blocked. Can you see that? It's blocked. This is blocked. So nothing can go there. Nothing can come. So here is Z. So Z is actually a real value that you can assign in Verilog to wires, to signals, Z. Okay. Why do we need it? So you will see if you want to, this is a, let's say 32-bit bus. Then if you have source 1 and source 2, sometimes this one want to put something here, sometimes this one. So what do you do? If this one want to put something in the bus, here you set this to Z, means this is blocked and now this one can talk, right? If you want S2 to talk, you put here, you connect, right? There's a switch you connect, a transistor is a transistor. You turn the transistor on and then you put this Z, okay? Remember this in your head, okay? Transistor is like a switch, okay? So I can just turn this off and on by my hand, mechanical, or if I need something like this, I can use transistor. You know about this, right? Transistor is switch. That's why we call it switch. We call it switching circuits, right? Circuits that switch, okay? Transistors have 2 jobs, switch or amplify. Amplify, okay? So what is amplification? You have a transistor. You put a small signal here like this on this pin, and then you get something like this. Like this. Oh, yeah, big one. Very small here, but at this point is very big. What did you do? You amplify. Okay. Another thing is this become like a switch. So you put some current here, and if the current is large, boop, this switch will be closed. So whatever you put here, for example, 12 volt, here will be 12 volt. If you close it, then you can actually put some pull down resistor here, like this. If you open this, then here from 12 volt become 0, ground. It will be connected to ground. Anyway, so I keep talking about this thing like crazy people. Anyway, so with this, now we know the literals, right? Yeah, because this thing actually needs a lot of effort. So let's have a break. Now it's 2:45, and let's come back at 2:55. Then I think, yeah, we need like maybe 1 hour. Let's see. And then I will teach you about this behavioral data flow get level, and then we have to actually switch to simulation, real simulation. Okay, see you. Do you have any question? 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 No question. So see you. Ding, ding, ding. Okay, sorry, I had to extend a little bit. I had something to do. Okay. Let's start. Slowly is 2.59. Are you guys here?
Yes.
Yes. Okay, so let's start. All right, so let's see what do we have here. So we have to write Verilog, okay, but the way that we write the code can be in three different, it's actually totally different from programming language. Programming language is just one way, you just write, okay? Actually, over there also we have different ways too, but the one we have is just one way. We learn it on the graph. But here we have three ways: gate level, data flow, behavioral. Okay. Now, before getting into the details, you have to know the meaning of this thing: logic synthesis. So the formal definition is this: when there is a software, a CAD software, okay, that can generate logic gates from the data flow or from the behavioral, okay? So you just give the behavior of the circuit and it can generate it. Generate what? A logic gate. Really? The answer is yes. Like what? You say, I want a 4-bit adder, and then it gives you this automatically. Can you believe that? It can do. The process of you writing the code, okay? Writing the code in Verilog, and then get the hardware is called logic synthesis. Now, this is actually what happens in reality. A human being, an engineer, right, start to think here in his head, and then he or she writes HDL code. And then that HDL code will be given to a CAD software. And that CAD software will produce logic gates. These are the gates. The circuit. And the process here is called logic synthesis. So you give your idea through HDL to a software, and the software will give you the gate. Amazing, isn't it? It's amazing. Then this synthesis actually can be implemented on what we call a chip that is able to be programmed. So we call it a programmable chip. And it looks like this. CPLD. It's called CPLD, but I will give you the definition later. It looks like this thing. So what if it cannot be programmed? What if we don't have this technology? Then the CAD software generates a file that you give this file to Foundry. Foundry, we call it Foundry. Is the word for IC manufacturer, okay? And then they will give you an application, a specific integrated circuit. They give you a chip basically, but this chip is the final version. It's like a processor, like a chip. You cannot change it. So what is a Foundry? Oh, that's it. Yeah, it's look like a facility like this. There are machineries here. You see the ovens and stuff like that. They put the layers on top of each other. It's actually a very complex thing. To construct this thing, this is a foundry, right? It needs $20 billion, approximately $20 billion. So it's not a job that I can do or you can do or even a university can do. It's a governmental project. It's high level. So a nation must decide if they want to have this technology or not. $20 billion is a lot, okay? So when you have something like this, then you design, you give it to the CAD, and then you give a file to this manufacturer. Now, a similar thing happens when you design PCB. So you use the ORCAD. How many of you know ORCAD here? Look like this. It's a software you design, okay? You just design the routing, the wires, and the layers. You see, here, look at this one. This is an ORCAD design. So it has actually two layers, the green layer and the red layer. Can you see that? And then you make holes and you connect the components together. So if you design this, you send, I think, even in the morning I forgot the name. I think they call it Kerber or something, Kerber files. Kerber. You send this some design files to PCB board manufacturer. In Thailand we have, yeah. So you see, you give to some facility and they make the boards exactly like this. Each board is, they can even make one for you, only one single board. It's like 100, 200 baht. It's not expensive for a 2-layer. But if you want 20 layer, maybe it is become expensive. Okay, yeah, the boards like this. And then you have to use a machine like this to place the, we call it PCB component placer. Placer. Yes, you see, yeah, machine like this, okay? You put the board here and then the components will be placed automatically like this, you see? So this is the same thing. But here, instead of the board, we have the hardware. Now, what happens if you design something, you generate the file and you give it to this. This, your chip, right, for one run is $10 million. $10 million. They give you the chip back and then you find that there is a mistake. $10 million lost. Can you believe that? Because you cannot change this chip, right? So in order to solve this problem, they came up with these programmable chips. Okay, now here you write code, which is actually the hardware. You give it to the CAD synthesize logic gates, but instead of putting them on the chip, you transfer them to a programmable chip. And you can actually keep changing this, keep programming. When everything is okay, then you go to production, okay? So now, with all these things in the background, we are going to implement our next design, which is a 4-input multiplexer. Now, what is a 4-input multiplexer? It's like this. It has 1, 2, 3, 4 input, 2 selector, so 1 output. If here I put 0, 0, is 0, 0, this will be connected to output. If I put 0, 1, this will 1, 0, this will 1, 1, this will, right? Now, question, how many input do I have for a 4-bit multiplexer? How many input? Let's see who is listening. I'm a puppy girl waiting for your answer. Come on, tell me how many input. If 16, 8, no. You can be wrong, but it's okay. No, 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 no. It's not for 12. How can you get these numbers? How can you get it? I'm a puppy girl waiting for your answer. You can be wrong. You are so wrong. Oh my goodness.
Sorry, can I see the schematic again? Oh.
You can see the schematic now, but only for a few seconds. 6. Okay. City. Yeah. Okay. City is right. City. Okay. L dot. 6. Okay. So this is 6. It means if you want to 6 one output the function f. So basically this is a combinational, right? But it's 6 input. But in this course, even in DLD, they teach you up to 4, right? So how you gonna have 6 input, 1, 2, 3, 4, 5, 6, and then function f, and then you have to make a k-map. It's so difficult to optimize, right? But let's say we actually could do it. And we optimize. It's difficult, but it's still possible, okay? And optimize, and this is actually the answer. Is still possible, okay? But so difficult. So we use a pen and pencil. We have a truth table, k-map, and then this is actually the answer, okay? Now I have the schematic. How I am going to transfer this into that programmable IC using Verilike, okay? The answer is this. First, let's try gate level. In gate level, I just pay attention to the gates and I try to implement the gates. Look what I do. This is the mux, okay, module. This is gate level, right? So I define the input A, B, C, D. This is the selector 2-bit, and this is the output, right? Now, this is actually the gate, and this is the instance name. This is the output of the gate, and this is the input, okay, input, output. So remember, always the first argument is the output. Now, basically what it does, it gets the select 0 and B means bar, right? Select 0, bar, like this. And it gets the select 0 inverted and outputs it here. But select B is a wire. So actually, by writing that, here becomes select 0B. Is the name of this wire, okay? How many inverter I have? 2. 1, 2. Next is the AND, 4 AND. You see? 1, 2, 3, 4. What are the outputs? N0, N1, N2, N3. So basically, I give a name to these wires: N0, N1, N2, N2, N3, right? Then, now, for example, I want to NOR them, N0, N1. Look at this, NOR, right? How do I do that? Look, NOR, module. This thing can be anything. It can change, up to you, okay? N0, NOR with N1. The answer goes to X0. Can you see? No. So this is actually X0. X0. This one is X1. So what is this OR gate? X0 with select 0. So I define OR X0 with select 0, again to Y0. Finally, Y0, 1, Y1, NAND together. See? So this is Y0. This is Y1. And this is called logic gate level implementation in Verilike, okay? You can implement any circuit. Just use the gate name Okay. If you need 2 input, this is 2 input. If you need 3 input OR gate, you just put a comma. This is I think, am I connected? I think I just gone
Yes.
for a few seconds, right? Okay. So if I need 4 input OR gate, I can continue like this forever. Okay. All of them will be OR together, and the answer will be here. All right. So let's count the number of lines. How many lines? You can count it. Okay, you can count the lines. You can count. It's 15 lines. I count already in the morning. Okay, from here to here, 15 lines. Now the question is, first, it's very actually lengthy. Another is that if I show you this code, can you tell me, without reading the name of the module, right, what it does? No, right? And if I make a mistake here, for example, N0 become N1, then you cannot find the mistake, right? Typo maybe. You cannot, right? That's the problem of gate level. Now, how to solve it? Another solution later on, you know, in 90, 70, 80, they tried like this. Then in 1990s, they said, better we come up with another way. So Verilog is actually changing too. So similar to C. How many CS standards do we have? You see, initially was ANSI C 1999, C99. This is 2011. This is 2017. You see, the C language changing. Okay, similar here. The Verilog changing. Now they said, now we're gonna have another one, and this is we pay attention to the flow of data. Can you see the flow? It's like this, right? From the left to the right, right? So say hello to assign keyboard. If you want to implement a circuit using data flow, you use the assign, and then this is the flow. The right hand side will be evaluated and will be placed into left hand side using assign continuously all the time in parallel. So these 3 lines will be executed in parallel. It really doesn't matter where to put them. The order does not matter. Now this is inverter. This one is AND gate, and this is no OR. Okay. So this is actually the equation. Select 1 and C is here. Select 1 and C is this AND gate. Can you see that? So I can actually just have one assign, but it would become very large. So I came up with, I say, okay, this is T0, this is T1. So everything here and everything here, and then I AND them. Does it make sense? But the approach, because I use the assign, is called data flow. Now, how many lines? 4 lines. Much better, right? This is 4 line. This thing is 15 line. Which one is shorter? Data flow, right? But if I tell you, hey, look at this and tell me what it does. Can you tell me it's a multiplexer? No. No. That's the problem. So when the circuits become very complex, after 3 weeks, 3 months, 6 months, when the designer come back, they don't know what the circuit is. They don't know anything about it, they forget. So they say, let's come up with a new way or new approach, and that is behavioral. Okay? In this approach, we don't care about the logic nor the data flow. We care about the behavior. Say hello to always block and register. Okay? For data flow, we use assign. For behavioral, we use always. Behavioral, always. Put this in your head. Behavioral, always. Behavioral, always. Behavioral, always. Behavioral, always. Okay? So behavioral, quickly. Always black. @ sign, this is called sensitivity list. Sensitivity list means you are not telling the cat software, hey, Mr. Software, Mr. Cat, be sensitive to a change that might happen on A signal, B signal, or C or D or select. If any of these signals change, you execute this block. So if A changes, this will be executed. If B, same, C, same. So basically, every signal here changes, this will be executed. Whatever is after begin and end. This is the mark. Begin is like this, end is like this in C language. Curly braces is just the starting and ending points of a block. Okay? Now, here, look, I have some bunch of if and else statements, right? It's like C, but it's not C at all. I say if select is 0, output is A. Select is 1, output is B. Select is 2, output is C. Select is 3, output is D. Now I set output and I declare the output as the register. Now, every time you see the register, you replace this with the word variable. Okay? It's just you have to do it. When you set a signal inside an always block, you must declare this as reg. Is the law of Verilog. Okay. Why, you will know later on why, but basically it's like you try to tell the CAD software that this thing changes. You see, it changes the variable, right? Sometimes it's A, sometimes it's B, sometimes it's C, sometimes it's D, right? Or when you write something like this, no, it's not 4 lines, it's actually 12 lines. So the code is a little bit longer, but now if I tell you, hey, what does it do? You actually can, within 10 seconds, you can tell, right? So easy, it's a multiplexer. You can actually see why you can say it, because you can see the behavior of the circuit. There is no logic gate. But this is like a jargon thing, like it's like encrypted jargon nonsense stuff, right? What the hell is this? Who can know? Nobody can know. But if I show you this, then you can know, right? So it really doesn't matter. You write a code like this, or like this, or like this. You will get the same circuit. Magical, right? Same thing. You will get a 4 input multiplexer. Okay? Now, knowing this, let's jump. Actually, if you were in the lab, I would tell you to go and pick the IC, right? So we have this programmable. This is what we call the programmable IC, and there is a technical term for this. We call it complex programmable logic device, CPLD. You can search for it. They use it in automotive industry, CPLD. Automotive design, yeah. You see? So when you look at the datasheet, you see automotive CPLD means they use why? Why is that? Because this is the IC, right? Basically, this IC, I can define the inputs like this. Is programmable. I can program this to be an AND and output. Can you see A, B, and F? I can design this circuit like this using HDL, and then I can program this IC to behave like this. And if I can place this in a car, and then one signal comes from one sensor, another from another sensor, and this is actually fast, is in the scale of nanosecond, I can get the answer within nanosecond. I can do a lot of things here, get the answer. Now, this thing is input, I, this thing is output. So we call it I/O. So every chip, you see the pins here, these are pins, right? This is actually low resolution. Can you see the pins? These are the pins, right? It's limited. So based on the packaging, the number of I/O is limited. Now the one that we have, you have to pick the IC and you read the number here. There is a number here. Okay, you read it. It's actually this number, XC2C256. So XC, yeah, this is the IC that we have in the lab. Okay. Now let's find the datasheet. So there are a lot of things. For example, it says it can operate at this voltage. And look, if you have 144 pin, then it gives you 180 I/O. Means here I can, you see the I/O, I can have 180 I/O like this, and I can, for example, pick this is input, I can AND this, okay, and then another input, I can OR this, okay, and then another input, I can invert this, you see? And I can make actually very complex designs, and then this is the output. Does it make sense what we are doing here? We program the IC. The IC inside have elements that can be changed to AND or whatever that I want, okay? And I can have my circuit. This is actually very powerful. It's so powerful that you can use it in military. For the missiles, you can use it in aerospace to control the planes, everything. Because this hardware is so fast and you can get the information and compute and send output. They use it for missile guidance systems, many things. So look at this is the packaging, TQFP. So what is TQFP? Is this, you see? Q stands for quad, flat package, so it's like this. So 4 sides have pins, okay? So you can actually see the list of IC packages or IC package. There are many, you see? So here, look at this. The TTL IC actually is deep. Can you remember deep? Means dual, it's like this, right? This is TTL, right? And then the transistor is usually the packaging is TO. The one that we have in the lab is TQFP, you see it's flat. But you have also QFN too. So the pins are under the chip. You cannot see this is on the side, this one is under. There are many, okay? Each one of them has a name. You will learn them slowly, okay? Now, these ICs are TQF, okay? Now, let's see how much is it. So, XC. So I want to buy this. Shopping. So this is actually, the IC itself is 200 baht, okay? Now, if I get the IC, how I am going to use it? I have to connect, you remember for the TTL? Connect the VCC, okay? So I go to here. Actually here, there must be a pinout somewhere. This one. So somewhere here, I must say, this is actually the speed of an OR gate. You see, it's very fast, 7 nanoseconds. Yeah, here, pinout, is it pinout? Yeah, you see the pinout? Okay, so it tells you about, if you have, for us it's TQ144, right? So it tells you which pin is which. For example, the VCC, let me see if I can find the VCC. Yes, you see, three pin, pin number 1, 37, and 84. I have to connect to VCC. And ground too. You see how many ground it has? Woo. A lot of grounds. So look at the pin, look at the IC, it's so small, right? How I am going to connect it? I have to actually design a board. Look at this one, this board, right? This board. I have to design something like this. Now this board actually, it connects it for me. This is called development board. This is the chip. If I don't have a development board, I have to make one myself. It takes time, maybe 1 month, 2 months. I have to design the PCB. But instead of that, I buy the development board and it's printed for me. And you know, everything, the IC pins can be accessed. I will show you. So the development board for this IC, the one that we have in the lab is called Tool Runner. So there are two different things. IC is totally different than development board, okay? So for this IC, you see the IC is made by Xilinx, but the development board is another company called DG something, DG Length, okay? So this is the board that we have in the lab. Now what they did, they put the IC in the middle and then they connect the pins to this. Can you see these black ones? Actually, they can let you connect other devices to this board, okay, through this. And then you have 7 segments and some push buttons and toggle switches and USB port for programming this. So this is called development board. Now this thing is around 1,700. So the IC itself is just 100 baht, but the board is around 2,000 baht. Okay, this is the board. Now let's look at the data sheet of the board here. You can download online. Okay, so yeah, that's the data sheet. So it tells you this is the IC, the blue one. It's connected to 7 segments, to push buttons, to LEDs. You see this? These are called PMOD, means peripheral module connectors. It's here. This. So why do we have this? Because if you pay attention, if I zoom in, right, you actually can. This is VCC. You can see this is VCC. This is ground. It provides power to the outside board, and then you can connect some other devices. Like what? Like for example, Arduino components. Yeah. Look at these stuffs here. Can you see each one of them? If I zoom, right, you see it has 3 pins, 4 pins, right? So you can actually connect these modules to here, to this. Okay, whatever that you want to connect, you can connect. Peripheral means some external, extra devices, helpers that you can connect. Okay, then you can have this expansion holes here. So if you want to get access to these pins, you can actually connect to these holes here. Easier, right? Easier. These pins are so difficult to have access to. Anyway, so this is the development board. Okay, with this understanding, now it's time to go and simulate Verilog code and some schematic for this. Okay, now if you remember, I told you go and find the simulator, right? None of you could find the simulator that I am going to show you today. Okay, and there is a big lesson into this. That some people, they just go and learn some online courses and they think now they are an engineer. They open a company. They tell everybody, I can develop a website for you. I laugh actually. And they, sometimes actually, my cousin was like this without any degree. Learn some PHP and HTML and CSS, and he could actually come up with some websites. But this is actually similar to what you did during the last 3 weeks. You just, you got online, you search, you got to this logic .ly, right? This one, logic.ly. This one. You remember you got this to the simulator? Maybe you got to this one and you thought that you are very clever that you could get to this one. And if you know you are on your own, maybe you start to implement very complex circuits there, but at some point you fail, okay? So some of these, self-learning developers, at some point they will fail, okay? But the problem is that they really don't know that they know nothing. They think they're like real engineer. So that's actually very dangerous. That's why when you have a company, I suggest you will know it by yourself when you finish your undergrad courses, that you just can't hire people without a degree because they don't know the stuff that you know. Now, a lot of people tell you, oh, this is actually nonsense. There is a discrimination between the people who have a degree or not, because actually that's true. The people who have no degree, they just don't know that they don't know. They just don't know, and they might think that they're very actually good. But the code that they write for a web page takes 10 seconds. But if they give it to you, you come up with a little bit different code that takes 10 microseconds or maybe millisecond. Same thing, but this is uneducated guy, knowing nothing about optimization, knowing nothing about multi-core, knowing nothing about parallel programming, knowing nothing about advanced techniques, knowing nothing about server unloading, knowing nothing about load reduction, knowing nothing about recursive algorithms, knowing nothing about stack load reduction, knowing nothing about those stuffs he knows nothing about. He just knows how to write some stupid PHP code. But if you become a CE student, then you actually know how to write, for example, multi-threading. So instead of you do it in one thread, you do it in 8 cores. So all of a sudden, this will be divided by 8. Then instead of, for example, this stupid sequential approach, you use another approach, recursive approach. So this thing will, instead of 1 million, 10 million loops, you do it in 100, iteration, 100 iteration. Here, it has to go 1 million. So similar to what I explained here, you couldn't come up with a simulator that I'm going to show you, right? And it's not your fault. It's because it's like industry is the top of the technology. Academia is a little bit behind. And the world, whatever is outside, is just junk. People don't know. So either you have to be in the industry or kind of like come to some university. Otherwise, you just can't. You just can't. Okay, so now let's see what's the real industry level simulator, okay? The real one. That when I show you, you will trash all those simulators, okay? Say goodbye to this one, okay? So what you have to do, go on Google and type Xilinx, ISE, download, go to this one. Now, this website, I'm gonna show, paste you the link here. This is from now on, our simulator will be this, okay? And you have to download the 14.7 version, nothing more, nothing less. This is the version, okay? And if you have Windows 10, you download this version. Otherwise, Linux, everything else, you download the others, okay? Windows 7 is this. You have to register using your organization email. Because you are a student, you can use the Assumption University email. And then you have to have a license file too. But I don't want to explain those things. The file here is actually big. Can you see? Where is it? is 15 gigabytes. So I actually can download it, for my internet is fast, but I can download it within 5 minutes, but the installation takes like 30 minutes. So I cannot show you the installation process. I expect you to, at least as an engineer, be able to install a program by yourself. Can you do that? When you face some problem, can you solve that by yourself? Like if it needs a license, if it needs a registration, if it needs you to turn an option on or off, just deal with that, okay? But if you got stuck, you can ask me in Microsoft Teams, okay? After you install, you will get this icon, okay? So let me turn this off. So you will get this, something similar to this on your desktop. It's called Project Navigator. So you run it, and this is actually a Linux-based software. And when you get into the industry, you will find all the professional software are written or targeted for Linux operating system, because over there we have the stability, everything, even the software that they produce the scenes for the movies, this American movies with high quality animation, the software is Linux based. You have, for example, the Cadence, the software that for designing IC, this one, Cadence. This software, you see, this is for designing IC. This is also Linux based. This one that I'm showing you also Linux based. And as you see, I don't have the Linux, right? I have Windows 10. So there is a virtual box installed first. Can you see that? There is actually, this thing is Linux. So this is like an operating system. Can you see the virtual box? Virtual box, right? So inside this, I hope that you know what is virtualization. If you don't know, go and find yourself, okay? It's not related to others. So inside this, now I have a software. Can you see the ISE? I can actually close it, you see? And this is actually my software. It has analyzer, impact, whatever, but this is the one we want, okay? You open it. This is the version, okay? You run the software, and you should see something like this. When you run it for the first time, you should see something like this, okay? Let me get some water. Hold on. Where is my thing? Hold on a second. Okay. All right, I'm back. So the first thing that I'm going to show you is to enter a design using a schematic. You have to draw it and then simulate. After that, I'll show you how to code in Verilog and then simulate. Then I explain the experiments and then we are done. Okay, maybe 20 minutes more. So the first thing you do is to get familiar with the environment. You have a bunch of menus here. Okay. Then you have a toolbox. Now it's inactive, most of the things. Then the window is divided into three. One pane is here, another pane is here, and then you have this one. This one is generally the output, error message, warning, search outputs, and console, okay? So 1, 2, 3. Now here, we deal with the project, related task, like new project, okay? Then I give, for example, section 642, 2/21, 1/2021, and say hello schematic is the name of my project. Okay, you can select where to save it. and this is your working directory. You can just type whatever here as a description to your project. Here is important. If you want to write code, you pick HDL. If you want to draw schematic, pick a schematic. So the first I pick a schematic. Next, now here, because this is the CAD software, want to program your chip. It says, tell me what is your chip. So Cool Runner 2, this is the chip. You see, XC256 is actually the chip that we have in the lab. You see, XC2C56, okay? And the packaging is 144. So that's why here, packaging 144, can you see? Package. The speed, actually a speed is also there. You cannot see it, but a speed is somewhere here. It says 7 or 8. It's on the IC. Anyway, 7 or 8. Okay. So the simulator, we have a lot of simulators. Model sim, you have to buy it. iSim is free. What language? Verilog or VHDL you can choose. Okay. And that's it. Next, this is the description and finish. Now I have a new project. This is my IC name. I click on it. Okay. Right click, new source. And here I want a new schematic and I call it top. The reason I go fast is because this is recorded. You can watch it again later on. Okay. So top, next, finish. Now I have a drawing area will be given to me. You see, 1, 2, the boom, here, okay, here. So this, let's close this. This is design summary. I'll talk about it later. So here, top.sch is the file. I close it, right? How to get it again? Implementation, top.ch, double click, I can get it again. Okay. Now zoom in, zoom out, or I can press the control and zoom in and out, okay? So what should I do? I should place logic gates. How to do that? Add symbol, or control N, or come here, you see the add symbol, click here, then you can pick the category, like what do you want? Buffers, counter, decoder, general, IO, latch, whatever, even TTL. It has, you remember the 193? It doesn't have the 93, but it has some TTLs. You can actually design your own too. But what we want is, I just go to all. I want an AND gate. I type AND. And I find the AND2, place, boop. See, if I want AND 3, means 3 input AND 3. This is 3 input. I want OR, I type OR 4. This is OR with 4 input. I want inverter, or inverter, I type inverter. I want XOR, I type XOR. XOR 2, you see? Oh, so the space cannot let me, I have to zoom out. XOR, you see? I want whatever you think, whatever you can imagine, they have it, okay? If they don't, even if you want something that they don't have, you can actually declare yourself, okay? So I can select like this and then delete this nonsense stuffs. Let's have our AND. So zoom in, this is my AND. You cannot connect anything to a gate, but through the wires. So I have to add wires. How to do that? Here, add. Can you see the wire, or press Ctrl W? Later on, you will be fast, you use the shortcut. Or here, add wire, okay? So you see, I click, you have to click on that square, okay? And then, bing. You see now, it says, do you want to go up or down? I actually can continue doing like this, okay? Like that. I can make a wire like this, okay? But I don't want to do that. So Control Z back. So here I press escape, then Control W or wire. And this is one, right? I don't want to continue, so escape. Again, Control W. Yes. And then this is wire. So I just connect 3 wires, right? 1, 2, 3. The next is to identify the input and output. So IO marker. I can use automatic marker, but you know, I want to show you how the input works. This is the input. You see, I go here and I click on this. Oh, oh, means the input. Now I mark. So what's the output? Output. This is the output, right? So now I have a module. This is my module. The input is defined to input. The output is defined, and this is the logic gate. Now this thing can be complex as hell. Okay. So you can, for example, I want to show you how. For example, put an inverter, okay, and then you can get the wire from here to here, okay, and now you can define another output. Right? So now it became, you see, more complex. You can have 1 million input, 1 million output, woo, whatever that you want. 1 million gates, okay? You can change the size. You see the size now is C. You can change it to here. Now it's 22 inch, right? Look at this, how big you can go. Ooh, now we are here. Okay, so, but I don't want to do this stuff, so I delete this. I just want to show you a simple thing, right? Oh, so connect this again. You see, be careful. Sometimes when you remove stuffs, right? Oh, so now I have to delete this. Things will be messed up. So this is the input again. Okay, now this XL, you know, the label is ugly, right? So I want to change it. So here, add net name. They call them nets here, or signal. Okay, I label this A. You see A, it become A. If I say Apple, it become Apple. Can you see my mouse Apple? So I just say A, and I click on the wire. This becomes A. B, F. F means the function. Okay, now I give them. You can actually, I suggest you to be neat and make it beautiful like this. Okay. This is my design. Okay. After this, I save it. Now this is saved. Next, look at this tick here. It says check the schematic. I click. You should get something like this. If you don't get, means there is a problem. For example, if this wire, I remove it, right? And I check. You see the error? Can you see the error? You have to fix this error. Okay. So Control Z cannot. So I have to delete this. Wire again. Marker again. Label again. B. Okay. Now this is, it seems okay. I save it. I check it. Okay, no error. Okay, when there is no error, I close this. Now I come to here, right? Right click here, left click, new source. Now my design is finished. I want to simulate. Simulation is here. Can you see the test picture? So I want to test the top schematic. I choose the top. Next, finish. Now I have to code here. Code simulation. So if this is closed, right, how you're gonna get it, the file that you created, you see there are two tabs, implementation, simulation. You go to simulation. There's a file that your test.v is here. Double click and it comes back. Okay. A lot of students cannot find it because they come here and there is, you see, nothing here. You have to select the simulation and then you can see the file. Okay. This says the simulation step is 1 nanosecond. The resolution is 1 picosecond. This is the name of the module. Don't worry about this thing. You will learn all of them. Input is register. Output is wire. My connector. Hello, my internet gone. Okay, can you see me? Can you hear me? Hello? Hello? Are you there?
Yes, Yes. Yes.
Okay. Okay. So this is this is my AND gate unit on the test. Okay. So I connect the pins. This is actually automatically connected. Be careful. You have to remove this. Okay. Don't forget to remove this and initial begin. Do whatever I do. Okay. And now this is what I want to do. Okay. Initially, I set both inputs to 0. Then after 100 unit time, this is how you do it. This is very large, but currently you don't know much, so you just follow me. Okay, I repeat this 4 times. So then I change this to 1, then I change this one to 1, then I change it to 1, 1 to cover all combinations, and I go back to 0, 0. Can you see that? Okay, so this is my code. This is my simulation code, okay, not implementation. Implementation was the schematic. Now look, here I save it, and I select the file. You see, if I select this, I cannot see. I have to select the file, and I can see this is my simulator. I expand, and I check the syntax first. Here I should see this green check, means the syntax is successful, okay? Then I simulate, double click on this, double click, and now you see another program will be executed, and this is the simulation. The real industry level simulation, okay, of a real digital circuit. So here you have this, the modules, for example, unit on the test. This is the signal A, B, F. You remember, 2 input, 1 output, right? And this is the waveform. Click on the waveform and then click on this full view, and now you can see 1000 nanosecond, okay? If you remember, every 100 nanosecond I change. Can you see that? Every 100 nanosecond the signal changes, right? And as you see, the only time that the signal is, the F is 1 is when both A and B is 1, right? So this is AND, right? It shows that our circuit is correct. So when you are assured of the correctness of the signal, if you want to give me, you actually have to give me the, this waveform. You come to here, print preview, and what I want is this, okay? You give me this. So either a screenshot or can print it into PDF, up to you, okay? But this is what I want. File, print preview, this is what I want, okay? And this is actually the simulation of AND gate, okay? Question? No question? You actually have to do it, okay? So this is being recorded, you do it by yourself, then if you have question, ask me in Microsoft. Now I'm going to show you, now I close the simulation, you see? I back to my software. Now I close the project. What is this? Close the project. Now I'm going to have a new project, and I call it this time, I call it hello very like. So this is 641 120 21. Okay. Now I'm going to show you how to write very like. This is HDL, top level HDL. Okay. Next. This doesn't need to change anything, and finish, okay? Now, this time, you remember last time I select a schematic, right? You remember that? This time I select Verilog module. Now, top, next. Here I can change the input output, but I will not do. Finish. So now I have a Verilog module. Look at this. The name, you remember the module and end module? And the name is top. So I will have A, B, and F. And I say input are A and B, output is F. So I define the direction. You remember in the schematic, I have to use the marker. Here, I just type. And then I will use gate level. Every time I write code, I tell you what approach I use. Here is gate level because it's very simple. It's just a simple AND gate. So I say and 0 is my instance name. Output is FAB. So simple, right? This is very like. Now I have my design. Now this thing can be as complex as hell, like this, right? Like what I show you here. You can write this, okay? Now actually that I show you, right? You can actually play with all of them. You can write this, right? You can write this. This is a module, right? You can write anything that you want. And now this is your design. Now, for today, our design is just one line. Okay. Then when you finish your design, you go to implementation, you select your design file and go implement design, synthesize, and here check syntax, save, and you should see something like this. Successful. You see, check syntax successful. It means now there is no problem here. For example, if you forget this, right, then you say check syntax. You see, you will get some error if you forget the semicolon or some problem. You see here. Okay. So what happens when you get error? You have to read it, right? You know English, right? Just read it. For example, here is a line 32, expecting semicolon. Can you see that? Found in module. So it means here you have to put here semicolon. The software expect semicolon. Okay. Check syntax again. Now my design is okay, right? Next is to simulate. New source. Now simulation is the same. So here I say test top. I select the top. Next, finish. Now look at that. Is this everything is the same? Now here you remember the auto init that was generated in pink color I removed. Here we don't have it. So initially AB is 0. Then I just copy paste this here. So look, AB is the same thing. I'm going to do the same thing. So copy paste this 4 times. Okay, initially is 0, then 1, then 1, then 1, 1, and then back to 0, right? Then save, I go to simulation, I pick this one, I simulator, I check the behavior. I want to check the syntax. Okay, now I'm ready to simulate. Run. Okay, same thing. I come here, and now again I see the output, right? Now I can actually quickly close, all right, and go to my implementation. Now I think my connection got. Am I online? There's a problem. Am I online? Hello, somebody says yes or no. Hello?
Yeah.
Okay. So I'm going to add an inverter. The F, right? So this is actually you're gonna wire. You're gonna be good at it soon. So I call it, for example, F temp. Okay. So initially I AND this. I put it here. Maybe capital F. It really doesn't matter. So F temp. So I AND this, right? And then I use an inverter, not 0. Okay. And F is actually invert of F temp. Okay. Just to show you, right? So basically you change your circuit a little bit, then you save, check the syntax. Okay. Then I go to simulator. Now I have the simulator already, so I just rerun more. Look at this. Now I change my design. I simulate. This is actually NAND, right? The NAND. Oh, F. You see? Now red signal. Something is wrong. A, B, C, D is okay, right? I don't get the F. Do you know why? I don't know. Let's see. So F is right here. Oh, can you see the typo? Can you see? Here is TMP. Here I put temp. Okay. Save. You see, be careful. Be careful. So let's close the simulation again. Did you see? You see, I got the red cut. Red means undefined. So in that case, you have to go and find the problem. So simulate again. So I simulate, now is green. Can you see that? Now is NAND, right? The only time that is 0 is when both of them are 1. So that's how we simulate. Now, let's go to the experiments. And if I repeat again, go to File, Print Preview, and give me this. You have to give me this. Okay, give me this. I need this. From now on, I don't accept anything else. You have to give me this kind of waveform from this software, okay? Now, let's see what are the experiments. And I'm getting really tired. So, this one, I asked you to know the development board, but you are not in the lab, so we ignore this one. This one, you remember last week, BC to X3 converter, you remember that one, right? Now your job is to put this into CPLD. So you, instead of TTL, you use the CPLD. So you have to code it. You have the equations, right? So maybe you should use data flow. Just here. So use data flow, okay? Like this. Data flow. This is comment, is nothing. Okay, so what is data flow? Assign, for example, F0, your equation, okay? And like this. It's very actually easy. F1, F2, F3. That's it. And then simulate and show me your simulation. Okay. Then next one, test this one, ignore it. You're not in the lab. This one, you remember the first week, right? Here now, you have to actually change the technology from TTL to this technology that I just said, tell you is CPLD, okay? How to do? Same. You have the equation, everything. You can go for gate level. You can even, you can go for behavioral. It's totally up to you, okay? You have to write the code or maybe draw the schematic, up to you. You have the schematic already, right? So if you go for a schematic, include the schematic in your report. If you go for code, give me the code, okay? And then waveform. That's it. And then you have a bunch of questions, answer. Finished. Questions. Let's go here. Let's go to Microsoft. Is there any question? Yeah, this is the software. This is the software you want. Okay, questions? No questions? Then we will close this session. Go download the software, install it, do the experiments, 2 experiments, simulate, attach the waveform, and give me the report next week. Okay, see you next week. Meanwhile, if you have any problem, you can just screenshot from your error message or whatever that you get, and then send me here, okay? If you send in public, is better. Don't send me in private. If you have a technical question, send in public so others also can see. Don't shy, okay? Others will have the same problem, but maybe they shy to ask. But if you ask, they can actually see and take benefit. I think public is better, okay? Don't worry. I know I don't know a lot of stuff too. So I always ask others, or I search Google. You know, it's just we all learning. I make mistakes. I don't know the stuff. You might be the same. So you just ask me in public, okay? Nobody cares. And later on, you know, everybody say goodbye to everybody. We're not going to see each other much later on after this course or this university. So don't care about others, what they think about you. Ask the questions. That's what I mean. Okay. All right. So good luck to you. Have a good weekend. And I'm online. So why everybody is quiet? I don't like it.
I'm here, sir.
Okay. Okay. So if we do, you have any questions? Talk to me.
Not yet. Now still downloading them.
Still digesting.
Yeah, it's still done. It's 15 gigabyte. Okay, it takes time. It takes time. Don't worry. Yeah, question, Eldad. Yes.
Like you just show us about how to implement the circuit using Verilog code, but the homework is about the counter. So we
It's
don't
about
have
it's not about the counter.
access. That's one BCD. So we don't know how to implement this one.
Why? Do you have the equation of this or not?
I do. I do have.
What is it? For example, F0 is A or B. That's the equation, right?
Yes.
For example, right? Then you want to implement it, you come here. You have to, you know, work a little bit yourself too. You have to work. So look. So first of all, I want to implement that one, right? I have A, B, C, D, F0, F1, F2, F4. Okay, so you have to write this. This is your top module. Then input will be A, B, C, D. Okay. Output will be F. All of this. Okay, let me copy paste. All right. So, do you have any problem with this? No. This is interface, right? So, F0. If you have the equation, for example, equation is A or B. Okay. So F0 becomes A or B. This is OR. How do I know? You just go and type Verilog operators. So here, can you see? OR. This is OR. This is negation, means not. Not. We have two kinds of OR: reduction OR and logical OR. Okay. So this actually is the job of your DLD instructor to explain these things, okay? So let's say another equation F1 is like this. A bar, for example, and what is and? You have to go to the, for example, this is and for example, C bar, okay, together, for example, or with D, okay? That's it, okay? This thing you make yourself, write yourself. That's it. This is your question number one, experiment number one. This is it, okay? Then you write this, then you simulate. And then you get a waveform like this, and then you go print preview, and that's it. And then what you have to give me in the report is this code, okay? And this code also you can actually either, I see, you know, you have to use your common sense. I see a lot of students, a screenshot, so funny thing. It's so easy. You either, you see, oh no, this one doesn't print. So you can actually, you know, copy paste this. It's so easy, you know. Copy, here, paste, you see? And then maybe a screenshot from this or print this into PDF file. It's so easy. Yeah, this one I teach you about, this is Notepad++, there's a plugin. If I actually save this into download and I give the extension V, it will actually so clever. You see, V, means very like it recognized. Can you see that? Wow. It actually highlighted the keywords. Can you see that? And module become blue. So Notepad Plus is very cool. It's very nice. And then you can put it in your Microsoft Word if you. So how to do? Plug in NMP export, copy all formats to clipboard, and then go to Word. You see, beautiful. Now I have the format. Can you see? So beautiful. And you can just give me the report like this. But if I just copy, you see, Control C, paste. Oh no. You see, Control C, paste. You see, it's not beautiful, right? And it's not colored. But if I go here, plugin, NPP export, all formats, then it will be colored. Can you see? It will be colored. Anyway, so questions? Did you get your answer, Eldad?
Yes.
Okay. So if you want to know very like, you don't expect me to teach you very like in like that. Actually, I teach you, right? But it's a huge language. You have to get the book. Okay. So go get the book. Talk to your DLD instructor, or you just search very like textbook. Not text editor, text book. There are many, you see, too many. And then I suggest you at least get three textbook, okay? You actually can type very like tutorial and start from somewhere, right? Yeah. Oh, this is actually difficult. Wait. Yeah, the problem is with learning online is that they randomly put the stuffs on you. So follow your DLD or follow the lab, okay? So let me look at this tutorial. Yeah, this is what I just taught you today. You remember the fabrication process? This looks a little bit better. Yeah, maybe you can follow these tutorials. So basically all is the same, but actually, Verilog is very complex. Be careful. When you get into some tutorials, they don't know your level and they throw at you a lot of complex stuff. You're gonna, your mind will be blown up. Be careful. This tutorial is high level. I saw. It has the delays. I saw the delays. Yeah, actually, it's a complex thing. Okay, so I suggest you start with my lecture note and then your DLD instructor, and then skip the tutorials are nonsense. I think textbook, maybe a textbook, yeah, and then read the textbook. I think the textbook is the best. Maybe this one. What is this? Yeah, something like this. Okay, but the best one is the one that I introduced to you. You remember? No. Go to course outline. Back. This one. Get this if you really want, if you feel lost, okay, and you don't know how to code, and there are 3 books here, you really have to read all of them. Start from this, okay? All right. Questions? Oh God! If no questions, I wish you good luck. See you next week.
Thank you, Achan.
Bye-bye.
Thank you, sir.
Take care.
Sir,
Yes.
can I ask you something about my scoring?
Yes.
Report.
Simulator.
Oh, wait.
Simulator. Simulator what?
Okay, sorry, I couldn't hear you. That's why. All right. I just want to know why do I got deduction in my week 1 report? If I get to the feedback session, when you put the comments, it says -1 for not submitting PDF.
Yeah,
But-
you have to submit PDF.
But actually, it's already in PDF.
Oh, really?
Yeah, I put .pdf.
Okay, maybe mistake. So let me see.
But I don't know why it might not be PDF. But yeah, I checked already. It's PDF because
Let me see.
I export from Notability and it goes to PDF.
Week number 1.
Week number 1, yes.
Your name is start with N.
Yes. Last one, .pdf. No, that's not mine. That is not Chapon. My name is Natashanon, the last guy.
Oh, last one.
.pdf, yeah.
You're right. It's PDF, right?
Yep.
Because too many students actually did not submit in PDF, so I copy paste.
And also,
Okay.
sir, the first waveform seems incorrect. You mean what you're referring to is the first experiment?
No, this one. Yeah,
Yes,
this one.
the voltage spikes, right? The one you mentioned.
So this one, what is this one? I don't remember. So you may follow this step, draw the twist. What is this one? This one is the alarm, right?
Yep.
So this one is what? You know, your problem is this, that you didn't identify the signal name. So I don't know which one is input, which one is output. So I consider red one as the output, and then it seems like which one is the output?
The output is the red one. It's actually identified by the color. Yeah, so for example, if you see,
I look at this, right? So if this is the yeah, that's actually maybe I got this one as the output. Yeah. Okay, so red one means if one or two is actually correct.
Yes.
Is actually correct. So 2 is operating, no alarm. Yeah, this is correct. Yeah. So yeah, this is correct. Okay, so wow.
And last one, sir, Q3 -1. I wonder why.
Question 3. Let's see. Question 3. Where is question 3?
Yeah, that one is question.
Yeah, where is the answer?
Below, sir.
I don't see. So that's again. Yeah, you see, I have to mark a lot of reports, right? So I come here and then I kind of like, where is the answer? I don't see the answer, and then I gave you more. Okay, so
yeah, it's right below, sir.
Yeah, it's here. I can see now. Okay, so this is the A. Yeah. So yeah.
Yeah.
So this is actually, so you will get 10. Okay.
All right.
Correct.
But
You
there's
got
one
2.4.
I just want to ask 3, because my simulation doesn't have the 7493 ICs. So basically, I will have to use MATLAB, right?
Yeah, you can use anything. That was MATLAB?
Yeah, but because I don't have MATLAB. Here's the thing, and
Yeah, but from now on, you use the one that I just told you today.
Oh, okay. So I can submit. Can I submit later? Because
Yeah,
I didn't mean that I didn't submit the latest one, but I already
Oh.
submitted without a
You
completion.
mean week number 2?
Yeah, the week number 2.
Yeah, you can submit later, but then I will consider it as late, and then you will read maybe 1, maybe 2, 3 points. I have to decide. Yeah, you can submit. So, for example, you can actually have no time until 4:30. You can submit 8 minutes.
Oh no,
But-
no, I finished, but incomplete. I didn't. I skipped
Okay.
1.2.2.
If the 4:30 p.m. deadline passes, okay, today is 9, right? Then maybe I cut a little bit. Don't worry. You can submit. Don't worry.
But the thing is that I already submit, but it's incomplete, right? So what I'm trying to say is that can I complete it later and after that send it to you by using
Yeah,
Word?
yeah, you can. You submit here. I think you can resubmit here. Okay. But if I grade, right? So this one actually week number 2, right?
Yes.
Yeah, you can do. You can do. Yeah. So resubmit and put the comment too, so I can remember. Okay. Because when I go through the reports, I forget. I don't even look at the name, so I forget.
Okay, sure. So let me just trying to learn what Verilog is, and maybe I will submit all together with next week.
Okay. Can.
Right. Yes, sir.
Okay. See. Okay. Anyone else? Anyone else? No? Okay. So see you and enjoy your weekend. The weather is very nice. Go outside a little bit, open your door, open your window and enjoy the weather. Today the weather is very good. Good luck. Bye-bye.